All right, shall we continue? So what I like to do when I'm covering L'Hopital's rule, I like to go online and just like do a Google search and find like a list of problems that I've never done. So that way we can kind of discover these together. So let's do, here's an interesting one. Limit x goes to 0 of, where was it? Oh, 3 to the x minus 2 to the x over x squared minus x. Remember, you can only use L'Hopital's rule if you have 0 over 0 or plus or minus infinity over plus or minus infinity. That's the only time you can use it. So you have to check first, right? So what is 3 to the 0? 1. What's 2 to the 0? 1. Okay, so 1 minus 1 on top, that gives you 0, right? So you have 0 on top, halfway there. 0 over, okay, bottom 0 minus 0, 0, right? So we have 0 over 0, we can use L'Hopital. So let's use L'Hopital. L'Hopital. All right, derivative. Be careful here. What is the derivative of 3 to the x? That's from last class. Don't tell me it's x 3 to the x minus 1. That's not it, right? What's the derivative of 3 to the x? It's self times natural log 3. What am I doing there? I'm using that thing a to the box, right? What's the derivative of a to the box? It's itself times natural log of a times the derivative of the box, right? That's what I'm using? Except I have 3 to the box. The box here for us is x. So it's 3 to the x, natural log 3 times the derivative of x, which is just 1. Y'all good? Okay, minus derivative 2 to the x is itself times natural log 2. All over 2x minus 1. Okay, now let x go to 0 again. You cannot use L'Hopital unless you have 0 over 0 or infinity over infinity. You must stop as soon as you no longer have that. So if I let x go to 0 here, we already said 3 to 0 is 1, right? So that's 1 times natural log of 3. Let me write this down. This is natural log of 3 minus natural log of 2 over negative 1. And that is not 0 over 0. That's a number, isn't it? Natural log of 3 is a number. Minus natural log of 2 is a number. And over negative 1 is a number, right? So that's just a number. That's my answer. Okay? Whatever that answer is, that's my numerical answer. I like that one. Questions on it? Okay, here's one that we've done something like this one before. Limit x is going to 3 of 1 over x minus 1 over 3 over x squared minus 9. So when x goes to 3, we get 1/3 minus 1/3, right? So we have 0 on top over 3 squared is 9, 9 minus 9 is 0. So we have 0, 0. We can use L'Hopital. 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 Okay, that derivative on top. I want to take a pause here for a moment because this is going to come up several times here in the next couple of examples. Look, if I have 1 over x and I'm taking its derivative, that's really x to the negative 1 and I'm taking its derivative, right? And that's going to be negative 1x to the negative 2. Just using your power rule, negative 1 comes down, subtract 1. That's negative 1 over x squared, right? Follow me? Okay, that's what that is. What would happen if I change that top to, let's say, any constant? What if I have a constant over x and I take its derivative? Same thing, right? The constant just comes for the ride. So wouldn't this just give me negative c over x squared? right? Isn't that what would happen? All right, keep that in mind. Right, what's the derivative of 1 over x? Negative 1 over x squared. Okay, minus, what's the derivative of 1/3? 0, okay, so that's that. Over, what's the derivative of the bottom? 2x. Okay. I don't think we have a problem anymore, do we? Because that's just negative 1 over 3 squared 9, and then over 2 times 3 is 6. Look at that as being 6 over 1, and then just flip it up. So negative, yeah, negative, well, careful. Negative 1 over 54. Right? So you keep this one, and you bring this one and flip it. It's 1 over 6 multiplied across. Yeah? All right, let's do another one. Okay, limit here, x is going to go to 0 again. We're going to go inverse tangent of 3x over inverse tangent of, let's go 5x. So the part about this that I think is a little tricky is, I guess, that you need to know what happens when you plug 0 into this. Right? So if you plug 0 in here, you get 0. Inverse tangent of 0 is saying at what angle is tangent 0? At 0. So you get 0 on top, and on the bottom? 0. So you have 0 over 0. Okay? So now I use L'Hopital's rule, right? L'Hopital. All right, be careful. What's the derivative of the top? We just learned that today, didn't we? 1 over 1 plus. Yeah, we're going to take the 3x and square it, which is going to become 9x squared. But then times what? 3. Don't forget chain rule. Over 1 plus. The 5x is going to get squared, but then times 5. You'll see that? Let x go to 0 now. That's 0 plus 1, that's 1. So you just get a 1 there, and you get a 1 there. So your answer is just 3/5. We're done. Any questions? All right. I think this one's going to be a little bit messy. Limit x goes to 0. I'm going to start with a fresh blank board here. Limit x goes to 0. All right, x squared times e to the x over tangent squared x. That blue's not too great. All right, let x go to 0 first, right? 0 squared is 0. E to the 0, what's e to the 0? 1 times 0? 0. 0 on top? Over, bottom? Tangent of 0 is? 0 squared is? 0. Y'all good? Okay. Can I use L'Hopital? Yeah, when you take these derivatives, you have a product rule up top, don't you? I mean, yes, you can do the derivative of top and bottom separately, but if the top is a product rule, you have to do the product rule. So I'm going to have to do a product rule here. And on the bottom, there's some chain rule. Okay, derivative of the top will be derivative of the first one times the second plus. Okay, so I did derivative of this times this. Now, what's the derivative of e to the x? e to the x, so itself, times 1, okay, and then times x squared, right? Then all of that over, now, how do we do derivative of tangent squared x? Chain rule. So first is the 2 comes out. 2 tangent x to the first power, right? But then times what? Secant squared x. Whoa, okay, that looks weird, yes? So I'm looking at this tangent squared x as this, tangent x squared, and then when I take derivative, 2 comes out, this to the first power, and then times derivative what's inside there, right? Now, hopefully, I plug in 0 and get an answer. Let's see. On top, 0 goes in, I get 0 there, right? 0 times 1, that's 0. Plus 1, right? E to the 0 is 1, times 0. That's 0 on top. Shit, that's not good. Okay, 0 on the bottom. I'm hoping to not get 0 here. Tangent of 0 is 0. Shit. What's secant of 0? 1, right? Because secant is the reciprocal of cosine. So secant of 0 is 1. 1 squared is 1. So that's a 1, that's a 2, that's a 0. So I have 0 on the bottom.
So we got 0 of 0 again.
We got 0 of 0 again.
So that means
So that means
we have to do.
you have to do L'Hopital a second time. Well, if you want to, I mean, what else are you going to do? Right? What else are you going to do? So we got L'Hopital a second time. Equals, by L'Hopital, limit x goes to 0. Okay, let's talk about the numerator. I've got to take a derivative. I've got addition right here, right? So I can do these separately. But that's a product and that's a product, isn't it?
Oh, damn.
So I have 2 product rules. Yes?
You could factor out the e.
I could pull out an e to the x on top and then still look at it as a product. That would be fine, either way. All right, here we go. Product rule on this one. Derivative of the first one, 2 times the second one, plus the derivative of the second one, e to the x times the first one. That's my product rule on the first, top left. Y'all agree? Okay, plus. Now a product rule here. Derivative of the first one is itself times the second one, x squared, plus derivative of the second one, 2x, times the first one, e to the x. Over. All right, this is the one I'm really not looking forward to. Because again, I have a product right there, right? I have this, I'm going to look at that all together, times this. I'm going to go ahead and attach that 2 to the tangent. Product rule there. What's the derivative of the first one? What's the derivative of 2 tangent x? 2 secant squared x times the secant squared x again. Well, here's one thing I'm happy about, is that there's a bunch of secants here, and I know that if I plug in 0, I get 1s for those, don't I? Okay, so I'm not so worried about that. Then, because of the product rule, plus, right? Now the derivative of the second one, chain rule, right? That's the same as secant x squared. So the derivative of that one would be 2 secant x, that's bringing the 2 out, secant x. Now the derivative of secant x tangent x. Am I done with this derivative?
No.
With this derivative, though, I'm done, right?
Oh, yeah.
Now I'm finishing up the product rule. So what do I need to attach to the end of that? 2 tan x, right? Who has a question about that one? I had a feeling this one would be ugly. It's living up to its... All right, I'm hoping for the best now. I'm going to let x go to 0 everywhere. Let me do it in a different color, because I know it's going to work. So e to the 0 is 1, right? 1 times 2?
2.
That's a 2. Okay, so far so good. Plus, this is going to be, yeah, that's 0, right? That's going to go away. That's 0, okay? 0 times 1 is 0. And then plus, okay, that's 0, isn't it? That's 0, and then that one's 0. So do I have 0 on top?
Yes.
No, I have a 2, right? I have a 2 on top. Ah, it's looking good. right? It's a 2 on top. 2 plus 0 plus 0 plus 0, right, is 2. And I'm hoping for not a 0 on the bottom. Now, we already said that this would be secant of 0 is 1, 1 squared is 1. That's secant of 0 is 1, 1 squared is 1. So this is 1 times 1 times 2. That's a 2 on the bottom. And then plus this 2 times 1 times 1 times 0 times 0. That's all going to go away over there, isn't it? But it's added, right? It's added. So that's a great thing. This is just 2 over 2. This is 1. The limit's 1. I would like for us to not lose sight of what we're doing here. If I go to Desmos, and if I were to graph this as a function, right? Y equals x squared times e raised to the x, all of that over tangent squared x, so I'm going to put tan x squared. If I were to graph that function, let's see here, and I were to ask you to find the limit. So remember, we're not doing tangent lines right now. We're not doing tangent lines. We're trying to look at limits. Where are we approaching? 0 from which side? Both, right? What happens to this function as you approach 0 from both sides? Where are we approaching? 1, right? Here's 0 on the x-axis. As we approach 0 from both sides, the function's value is headed to 1. What's the value at 0? It's undefined. And the computer would probably tell me that if I dragged over it right there. At 0, it's undefined, right? We knew that you couldn't plug 0 into this, but we know that the closer and closer to 0 you get, the closer and closer that gets to 1. It's pretty remarkable that we can figure that out without the picture, right? That we can figure that out with just, what, calculus, right? And L'Hopital's rule. What are y'all thinking of L'Hopital? Pretty good, huh? Pretty powerful? Don't sound so excited. All right, we need to keep going because we're just kind of scratching the surface here. Okay, limit x goes to infinity of 4 to the x over x to the 30th power. Here's what I'm going to do. I'm going to go to Desmos first. I'm going to go to a standard graph, and I'm going to type this in. 4 raised to the x over x raised to the 30th power. What does it look like is happening as I go out to infinity from this picture? What does it look like my function's doing? It's headed to 0, right? It's not. It's not. The picture makes it look like it is, doesn't it? Okay, but let's see why it's not headed to 0. As x goes to infinity, what's 4 raised to the infinity? Infinity, right? So the top's headed to infinity. Bottom, what's infinity to the 30th power? Infinity, right? Do y'all agree? We have what we need for L'Hopital. Let's do L'Hopital one time. When we do L'Hopital one time, what does the top become? 4 to the x times natural log of 4 over what? 30x to the 29th power. Right? Okay, what happens now? X goes to infinity. 4 to the infinity? Infinity times, isn't natural log of 4 just a number? So infinity times a number is still infinite, right? So we have infinity on top. Okay, infinity to the 29th power. Infinity, right? So you have infinity over infinity. We do L'Hopital again. Limit, x goes to infinity. Derivative of the top. This constant comes for the ride, right? So I just want the derivative of 4 to the x again, which is 4 to the x times natural log of 4, right? But I already had a natural log of 4 there, didn't I? So just square it. And then over on the bottom, 30 was there, right? I brought a 29 out, and then x to the 28th power. Yeah, so what's going to happen? Every time I do a derivative, what's happening on top? I'm going to get a 4 to the x, and then I'm going to get another natural log of 4 to pop out, right? Every single time I do this. Let's just try and do one more. L'Hopital, limit, x goes to infinity. So my next one will be 4 to the x, but then natural log of 4 to the what? Cubed, right? Because I'll have a third natural log join these two. Then on the bottom, I'm going to have the 30 times the 29 times the 28, and then x to the 27th. Are we still getting infinity over infinity?
Yes.
Yes. However, what's happening on the bottom? The powers keep coming down, right? The powers keep coming down. So eventually, I'm not going to have an x down there, right? Eventually, I'm going to get a what down there? Some constant. Do you all agree we do enough derivatives? Yes? Yeah, so it's going to be 30 times 29 times 28, and then eventually down to 1, right? And when you get down to 1, that's 30 factorial. So I'm not going to show any more. We're going to just, we're deducing this just by pure logic, right? This is going to head to 4 to the x times natural log of 4 to some power, right? I'm just going to put question mark, right? Eventually, we're going to have that 4 to the x with natural log of 4 to some power. And then on the bottom, we eventually get this down to where we finally get x to the first power. And on the next derivative, it becomes a constant. Make sense? So this is going to be a constant at some point. And when we get to that point, you can no longer use L'Hopital, right? But what's happening to that if you take that limit? Where's the top headed? Infinity. And where's the bottom headed? To a number. And what's infinity over a number? Nope. It's infinity. This keeps getting bigger, and the bottom is just stuck as a constant, right? So where does that ratio go? Infinity. What did it look like on the graph? It looked like 0, didn't it? This is an example where your picture, your computer is going to trick you. So the way to see what's happening, what I would have to do here is I'd have to go pretty far out to see it. There it goes. You see, I had to get far enough out. And so what happens is that eventually the numerator, see, x to the 30th power is going to turn into huge numbers, right? But 4 to the x grows even faster, right? So what happens is in the beginning, this dominates this because it's such a high power. But eventually, the exponential will overwhelm the polynomial on the bottom. That's why when you're studying college algebra, the idea of exponential growth, a to the x, versus polynomial growth, x to the n, you're told this grows exponentially, it grows very fast. It's because no matter what this power is, eventually this will overwhelm this, right? As long as that a is bigger than 1. And this is a good example, right? If I change this to 300, does it change our conclusion? No, right? It just takes a lot longer to get to it. If I change this to 3,000, doesn't change it, right? Eventually, take a 3,000 derivatives, 3,000 L'Hopitals, eventually the bottom becomes a constant. All right, that was a good problem. I like that one. All right. Okay, here's one that's kind of different, all right? Everything I've given you up to this point has been intentionally 0 over 0 or infinity over infinity, right? So that we can use L'Hopital's rule. I want to give you an example of something that's not 0 over 0 or infinity over infinity where we can still use L'Hopital, but we have to do some work first. All right, so here it is. Limit x goes to infinity. That alone is not enough for you to be saying, I'm going to use L'Hopital. Okay, square root of x squared plus 1 minus square root of x plus 1. Let's check first to see what's happening. This is becoming infinity. Minus, this is becoming infinity. That's not 0 over 0. That's not infinity divided by infinity, is it? So you cannot use L'Hopital's right now. I actually told you back in the day when we were doing limits that when you see infinity minus infinity, to try and factor, right? To try and factor something out. Factoring here is not that clean or easy. So what I'm going to do here is just kind of a trick. Show it to you, and when I show it to you, I think you'll be like, okay, yeah, I guess if you say, now I see you do that, I guess I could try and think that way in the future. I'm going to multiply this times 1, okay? I'm going to multiply this by 1. I'm going to multiply it by its conjugate over its conjugate. Do you all agree I'm multiplying by 1? So I haven't changed the problem, have I? That's still the same thing. Let's just see what happens. Okay, remember this is like over 1 and then I'm just going to multiply straight across. What's that times that? X squared plus 1. Okay, what is going to happen to the middle multiplications? This one and that one. They're going to cancel, right? That's the whole idea of the conjugate, right? So those two in red I'm not even going to do. And then I'm going to do the last two, which is this times this. I have a negative times a positive, so minus, and then what? Parentheses x plus 1, good. So you have to subtract whatever happens when these two roots go together. The roots kill each other off, you just get x plus 1, but I still have to subtract it. So that numerator is actually pretty nice, yeah? And my denominator is whatever it is, right? Square root of x squared plus 1 plus square root of x plus 1, like that. Are we getting infinity over infinity now? Let's clean it up. Limit x goes to infinity. Okay, on top I have x squared minus x, right? That's it? Over square root of x squared plus 1 plus square root of x plus 1. Okay, so I just distributed this through, went minus x minus 1. The 1's canceled out. I still had the minus x there. Y'all see it? No? Now I actually have infinity over infinity. Right? Well, is that infinity? Is that infinity? Isn't this infinity minus infinity? But remember I said that the squared will dominate the x, right? So that will, in fact, turn into infinity on top. And then on the bottom, infinity plus infinity. So you got infinity over infinity, right? Now you can use L'Hopital, right? I'm not sure where it's going to go, but let's try L'Hopital. I'm a little bit hesitant about this one. My instinct is telling me not to use L'Hopital right now, but I'm pulling this problem off of a website, so I'm going to see what happens. My instinct right now, is actually to come in here with 1 over x over 1 over x, and distribute through to try and kill off the highest power. That's my instinct, but I'm going to go with this. L'Hopital, derivative of the top is just 2x minus 1, right? On the bottom, you have two roots separated by addition, so you have to do chain rule on each of these, don't you? Okay, derivative of the first one. 1 over 2 root x squared plus 1, chain rule, times 2x, good. So that's derivative of this one, right? Derivative of square root of something is 1 over 2 times square root of that something times derivative of what's inside, which is 2x. Plus, derivative of square root of x plus 1 is 1 over 2 square roots of x plus 1. And then times 1. Okay. What can we do here? Well, you can cancel out a 2 here. You can't cancel these out, though. You can get rid of the 2 if you want. Let's just check to see what's happening. Can we see what's happening? What's happening right here? What's that headed to? Infinity. Okay, this one let's talk about in a second. What's this headed to? 1 over infinity. What's 1 over infinity go to? 0, right? Fixed over infinity, that gets small. So this is what we got. This right here is headed to infinity. This right here is headed where? 0. And then I'm adding to that, this is the one that's a problem because that's really what? Let's cancel the 2's. That's really x over square root of x squared plus 1, right? And what is that headed to? Infinity over infinity, right? Which means we don't know, right? So here's where we run into something that's really nice about limits. Are there any questions on any of this so far? That goes to infinity, that goes to 0, this one goes to I don't know, right? Infinity, 0, I don't know. The great thing about limits is that if you get something like this where you know what certain pieces of them are doing, and there's one of them that you're not sure, you can just go do this problem on its own. Let's go figure out, maybe we can figure out what that is by itself. And maybe if we can work that out, then we'll have an answer here. So I'm going to leave that here. This right here, I don't know what it is, right?
Can we ask a question?
Yes.